And we now have Nicolás Sirolli, who will be speaking on generalized theta series and the central values of Hilbert modular forms.
Okay, thank you. So I would like first to thank the organizers for inviting me. I'm really glad to be here speaking on science. Well, this is a joint work with Gonzalo Tornaría. Let me start by briefly summarizing what's the plan of this talk. So I'm going to talk about how to use generalized theta series to obtain half-integral modular forms and relate them to twisted central values of Hilbert modular forms, like the title said. So I start by going back to the history of this subject, talking about the Shimura correspondence between half-integral modular forms and integral modular forms. And then I'm going to recall Waldspurger's formula, which shows that the Fourier coefficients of the half-integral modular forms are related to the central values of the integral modular form equation. So this is kind of classical now. It's 50 years old, and there are many works on this subject. I'll focus on two previous results which motivate our work. These are the works of Gross and Shin Mao. In the work of Gross, he shows how to make this formula kind of more explicit by showing how to obtain the half-integral modular forms using a ternary theta series. This is a great result, but it's somehow incomplete because it's missing some discriminants. On the other hand, the work of Shin Mao show how to obtain the twisted central values for every discriminant. So, but this is the result is not as explicit as Crosby because they do not use theta series. They use an automorphic representation theoretic framework instead. So our goal is to do both things at the same time. We would like to obtain the whole family of modular forms from Shin Mao by using theta series as in Gross work. Actually, we're going to use a generalized version of his theta series. Okay, so let me recall a few things about the Shimura correspondence first. So we're going to work with half-integral modular forms. I'm going to stick to the classical statement here over the rationals. So these are modular forms which transform in this way with respect to the direction of the Congress subgroup. Where here you must take a square root, which has to be done with some care. Never mind, don't mind about it. The thing is that they are periodic, so they do have Fourier coefficients, a Fourier expansion. Okay, what Shimura proves almost 50 years ago is the following. If you have an f as here, which is an eigenvalue of the Hecke operators with these eigenforms, with these eigenvalues, then he shows that these are actually the eigenvalues of an integral modular form. So he defines G as the modular form which has this L series, and he proves that G is actually modular, which level with level the level of f divided by 2, and the character is going to be raised to the square. Well, so this is pretty much all we need from Shimura. In his article, he leaves a couple of questions. One of them is the following. He gives this formula which shows how the Hecke operators act on the Fourier coefficients. So the Fourier coefficients of the TP square acting on F has these coefficients. The nth coefficient is going to be related. The mu's belong to the F acted by the TP, and the lambdas belong to F. So the nth coefficient is going to be related to the P square n coefficient, the nth coefficient, and divided by P square coefficient. It's pretty much similar to the integral case, but we have these squares here. So the thing is that if you have an eigenform, then this shows that the Fourier coefficients are not going to be completely determined by the eigenvalues, as in the integral case. So Shin Mao leaves a question for us. He says, well, there's more information in the coefficients than in the eigenvalues. What's the meaning of all of the coefficients? Well, the answer is given 10 years later by Waldspurger, where he proves that these Fourier coefficients are related to the twisted certain values of an integral, the integral weight from G. So more precisely, once you fix a new formula G of arbitrary weight, weight and level, he shows that there's a family of morphomes, which I'm going to index by subindex gamma, whose Fourier coefficients are related in this way with the twisted set of values. And he shows that this holds for square free negative integers. Well, let's move on to the results of Gross and Shin Mao. So the work of Gross is about obtaining again Waldspurger formula in a somehow more explicit way, because Waldspurger proof is completely representation theoretic. He's going to show how to obtain these Fourier coefficients. Sorry, I'm going to back here. These Fourier coefficients as by essentially counting points on lattices. More precisely, he's going to build the one of the morphomes from Waldspurger, only one of them, by using a ternary theta series. So this is going to resemble a little bit the talk of Gonzalo. So I'll be more precise in the next slide, but he's going to show how to build having the way more forms out of ternary lattices. These ternary lattices are going to be the key ingredients for defining this object here. And the thing is, he's going to start from the morphome G. He's going to simplify things by considering prime level way 2. Then he's going to pick the quaternion morphomes in Shackle-Lange correspondent with G. That's quaternion morphomes with the same Hecke eigenvalues. And he's going to consider the theta series that we can obtain out of this one. And this is going to give us having the weight morphome of level 4p. And actually, it's going to belong to the subspace of the whole space here, the so-called Carnot class space, in which the Shimura correspondence divides the level by 4, not merely by 2. And this is how he's going to obtain this F here. So more precisely, he's going to fix the quaternion algebra ramified at P and at infinity. Here we are going to pick a maximal order R, which is going to have discriminant P. And I have to move this square here. He's going to pick a set of representatives for the, say, right ideals for order here. So, as we were saying, we're here going to, as in Gonzalo talk, we're going to consider quaternion morphomes, which in this case are going to be merely formal linear combinations of these classes. And given our formula G, it's going to be in Shackle-Lange correspondence with one of these linear combinations, which will have the same Hecke eigenvalues. So out of this phi, I'm going to obtain a Habsburg Waymo form F by combining linearly these ternary theta series, which are going to be defined in this way. These are going to be the theta series attached to the quadratic form minus the discriminant, which is going to be totally. Well, okay, it's going to be total. It's going to be positive definite once you mod out by set. So you can see on the left order of this ideal, and you consider this theta series, and what we prove that this thing here is modular of this one weight. So one of the key, one of the good things about this construction is that these weight coefficients which were involved in Waldspurger formula are completely, you can completely compute them effectively. If you want the minus d coefficients, all you have to do is to count all of the points in these lattice with discriminant d. Okay, so his results are the following. He shows that, we start with G, we define F as above. He shows that this Waldspurger formula holds not for every discriminant, but only for those which are fundamental. That's not a restriction, but he sticks to the negative ones, which satisfy this quadratic condition modular p. They can be divisible by p, and the correct symbol here must be -1. So this is great, but has a couple of restrictions. These are not real restrictions, as we'll see. But you don't obtain every discriminant because of this restriction about this restriction modular p and this restriction at the Archimedean prime. Furthermore, you have this extra term here, which could be 0, this main center value. So the thing is, if this factor here is 0, then this formula is not going to say much about these values. Actually, if this is 0, then these coefficients are going to be 0, and our molar of f will be 0. So let me go back a little bit. If f is 0, then it's because you're getting lots of cancellations when you count the point and sum them according to these coefficients. So to overcome them in a different way. That's something we're going to do later. So this is gross work. Let's move on now to the work of Shin Mao, which is we could say some. Oh, is it so? It's okay. You see me?
We can now. Yes.
Okay. Sorry. Okay. I saw blank screen. Okay. Okay. So the result of Shin Mao is a kind of a refinement of Waldspurger results. Let me be precise. Well, the level is not going to be completely shared. It's going to be all square free. The thing is that okay, we fix a new form G of level n, arbitrary weight, and what they show is that there exists a family of molar forms satisfying Waldspurger formula, and this family is going to be parameterized by certain choices of signs. So we're going to choose function gamma, which is going to be a choice of signs, one for each prime dividing the level, and one at infinity. And what they show is that you have a arbitrary molar form f gamma satisfying Waldspurger's formula for discriminants satisfying local conditions given by the function gamma. So these quadratic conditions, both for the Archimedean prime for these primes, do have to agree with the function gamma that we fixed. They even admit discriminants which are not prime to the level, so that's great. And furthermore, must say that the level and the character of the small form are completely explicit, and I'm not emphasizing it, but I don't need to. And they are determined by this function gamma. So let me say a few words about how they do construct these molar forms. Or the construction is purely representation theoretic. So they have G as their starting point. They consider the automorphic representation pi in which G lives, or actually the automorphic form phi lives. So a later work by Waldspurger rephrases the Shin Mao correspondence in terms of correspondence between representations for GL2 and a family of representations for the metaplectic group. So within this family, we have a distinguished member which corresponds to this choice of signs gamma that we have started with. And they define F gamma as a certain vector this representation. This is done by local means. They actually show how this correspondence is done locally. This is completely explicit in terms of the parameters described in this presentation. And then they can describe this one, and they pick a particular vector in this representation, and they define the molar form F gamma as a morphic form having these local components. So this is, of course, great and completely general in this terms, but does not allow us to compute the Fourier coefficients of this from here as we had in Gross. So our goal is to mix, to obtain a kind of a mix of both results. To be the bridge between them. So we would like to obtain this family of modular forms, which is able to handle every discriminant. We would like to obtain them as well by using a generalized theta series. Moreover, we would like to be this as general as possible. So we'll make this over arbitrary real number fields, which is, of course, needs a lot of care about technical details, but it's not just, not merely that. We will see that some new features arise when moving on to additionality. And we would like as well to make this work for more levels and not just all the square free levels. Okay, so this will be the setting. I'm going to fix a totally real number field F, and we will pick a new form G of in principle arbitrary level n arbitrary weight. Well, this is not completely sure. We must make some hypothesis here. We will assume that if the level sought, then the weight, the degree of the number field sought, then the level is not a perfect square. So as Ariel was saying a couple of minutes ago, this is not a hypothesis when you deal with quadratic fields. Well, this hypothesis could be removed in some cases, but I'm not going to talk about this. So we will, as in Gross, we will do the following. We are going to pick totally definite quaternion algebra containing an Euler order of discriminant n, the level. Okay. Here, by Euler, I mean a more general family of orders. I'm going to use an order which has non-zero Euler invariance at every prime dividing the level. Okay, so this is pretty much like in Gross. So I'm going to fix one of these functions gamma, which is going to be again a choice of signs, one for each prime dividing the level, and one for each Archimedean prime. And in terms of this gamma, I'm going to define two auxiliary parameters which are going to be used to define our Fourier series. So there are two parameters. One is a non-zero element. You can think of this as a discriminant. And the other one is a Hecke character. So how do they depend on gamma? Well, the auxiliary L has to satisfy these quadratic conditions on every prime dividing the level and the Archimedean primes. These are determined by the function gamma. And the character, well, in principle, it could be any character which is ramified outside the level, are also ramified on those primes dividing the level in which this condition goes in the Hecke values of she holds. And we would like it to be odd in the remaining primes dividing the level. Okay, so the main ingredients for obtaining a morph F gamma are the generalized Fourier series. So, Ayel, you want to say something?
Yes, may I ask you, in the previous slide, what is this E of RB?
Oh, it's the Euler invariant.
Okay.
Okay. These are the generalized Fourier series that we're going to consider. Okay, so the Fourier series is going to be attached to a lattice, ternary lattice, which is pretty much asynchronous. We're going to pick the left order of an ideal mod the integers of the number field. We want to deal with arbitrary levels, so we're going to need a harmonic spherical polynomial of degree k. But the key ingredient here is actually the wave function, which is going to be a function defined by the lattice, which is going to have values here. You might simplify things by thinking that here I'm not putting S1, but plus minus 1. Which is going to produce to cancel the cancellations that we saw in the crosswalk that might lead this construction to be zero. I'll talk about this a little bit later. This was one of the ingredients. The other one you can see it here is the number L, which is going to produce a new quadratic form here. Well, what we show is that these things here are modular with level controlled by the character. It's the least common multiple of the level n and the conductor of the character. So you might want to keep this as small as possible to keep this as small as possible. And a new feature here is that these are actually not necessarily holomorphic, but skew holomorphic, which means that it's going to be holomorphic at some variables and anti-holomorphic in the remaining ones. And that's because of this L that we put here, which make this new quadratic form not to be totally definite. It's going to be positive definite when else positive and negative definite in the remaining cases. So that's what skewing here. These spaces, this is something that we do not see in the classical case because of the following. These spaces of skew homomorphic morphomes can be put into correspondence with the spaces of holomorphic morphomes of the same level and a slightly different character. Whenever you have a unit whose signs agree with minus the function gamma that we have here. So merely by shifting by you get this isomorphism here. So you do not have units with arbitrary signs when the class number and the null class number do not agree. So in that case, you won't be able to obtain holomorphic morphomes out of these morphomes by shifting. Okay, I would like to say a little bit about these weight functions. I'm not going to be precise. I only want you to see what they look like. So these wave functions are defined locally as products of local wave functions, which are defined in one way or another, depending on you are inside the conductor of the character or inside this auxiliary discriminant L. So they are, here's where you use our auxiliary character, and here's where you use L. And they are defined by evaluating these characters at certain inner products, where there are some auxiliary vectors here. Never mind about that. This is what they look like. These wave functions do not belong to us. Originally, they were originally considered by Mao, Rodriguez, Villegas, and Tornaría when they were considering this problem in the rational case, in the case of prime level, and later on by Tornaría and Ariel Pachetti in the case of composite levels or the rationals. So they produce this construction in this setting, and they show experimentally they show some experiments in which they verified by Waldspurger's formula. So summing up, I'm going to consider here automorphic forms over the quaternion algebra. So I'm not sticking to the weight 2 case as in Gonzalo's talk. I'm here consider functions in the idealized quaternion algebra having values in the space of polynomials. Well, these automorphic forms are going to be automorphic. They're going to be invariant by the idealized units of the order, and the local elements are going to act in this way. So these are the automorphic forms in the quaternion algebra. And we reproduce here the picture I've shown you before. So again, we start with our new form G here. Thanks to the hypothesis we made on the level not being a perfect square in the case of all degree, then it's going to correspond with an automorphic form phi capital 1 actually via the Shackle-Langlands map, and by corresponding I mean this has the same eigenvalues as this one. And what we do is we define a map from this space. I've shown you before how to define it on ideas. Well, we mix all of mix all of these theories into a map here, which is Hegelian actually, and we obtain out of these quaternion morphoforms arbitrary morphoforms. Skew ones actually, and the Conan space is still we would say under development in this shown setting, but I mean only the case of holomorphic morphoforms of either trivial or no square field level has been considered in this case, and we've shown that. Our construction lands inside this Conan space. Okay, so that's how starting with G we obtain a more form F gamma. So this is our result. The formula resembles both the result of Ross and the result of Bach and Mao. So are having their way more from F gamma satisfied the following formula relating the twisted central values of G by three coefficients of F gamma. This is going to hold for those fundamental discriminants of type gamma, which means the quadratic conditions on the primes dividing the level and the intermediate primes are determined by the function gamma, and we are able to prove this for discriminants which are not prime to the level under some conditions. Okay, so there are two conditions that we were needing for this to hold. One of them hopefully will be delayed in the future. We are having some trouble handling even discriminants at even places, but this is going to be solved once we take care about some even primes are always more difficult, and we have to deal with them with some standard representations in the even case. The other constraint we have here is that primes not discriminants not prime to level have trouble when the valuation of the prime at n is bigger than 1. And this is a truly problem of this construction, because we actually show that these vanish every time. This always vanish in the when this is bigger than 1. So to handle these ones, we have to do something different, either consider a new family of weight functions, or apply our results to a proper to an adequate twist of shape. So going back to gross, as you see here, in the case of gross, you had L equal to 1. Here you have this extra factor, which is the central value of G twisted by auxiliary parameter L. Well, of course, this is everything is going to be meaningful as long as this is not 0. Well, the thing is that we can actually choose L in a way that this is non-zero, as long as the function equation allows so. As long as the function gamma that we consider here is such that these members here do not vanish trivially because of functional equation reasons. If gamma is such a function, then we are going to be able to choose L in a way such that this does not vanish. So this formula is then meaningful. Okay, so let me say a few words about the proof. Really few words. Our proof follows the ideas of gross, in which a third component, a third ingredient is used to relate Fourier coefficients with central values, and it's kind of a geometric ingredient, which are special points on certain curves. So our results are based on the formula by Shan, which relates these twisted central values to these heights of special points. And what we do is we relate these heights to Fourier coefficients. Okay, that's hard work, and summarizing this arc here. So I'm not saying much actually. So one problem with Shan's formula is that it's going to relate both things only in the case of discriminants which are prime to level. So in those cases, this does not work. So what we have to do to be able to handle this case is to prove a formula like this one I have here. This small dot is because I'm omitting some factors which are not meaningful. So this formula, which is already present in the Waldspurger work, relates central values and Fourier coefficients of two discriminants as long as they belong to the same type gamma, either whether this symbol is here is 0 or not. So once we obtain a formula like this, we are able to prove the formula for D2 as long as we prove it for D1, and as long as D1 is prime to level, the formula holds. So this allows us to obtain the formula for D2. So this equation is proved by showing that the quotient of both members is related to certain local values of the Whittaker functions at the vectors matching corresponding to our modular form. So this is what remains to be done in the even case to be able to handle even discriminants at even weights. Okay, I'll stop here. In this web page, you will find many examples in which we've shown our formulas in action. So that's it. Thank you.
Questions for Nicolás?
May I ask you a question, Nico? So
Sure.
in your main theorem, you said that there is a big obstruction when the valuation of n is not 1. Why do you say that the construction is 0 in this case? I mean, maybe I understood it wrongly. I don't know.
We first verified that experimentally, where we saw that if the evaluation is 2, then discriminants which were not prime to this prime will not appear in our forms. And later on, we proved that we've shown that this vanish every time. This does not hold.
Okay, so
they're not going to appear. So we do not expect this formula to hold, because this will be identically 0, but this could not be 0.
So this is in the case where you have a prime which divides both the level to the second power and the discriminant.
Exactly. Yes.
But this is not a ramified prime.
It could be ramified.
It could be non-ramified. So and do you have an explanation why this sum is 0 in your case?
Well, not only the sum of is 0. We've shown that in each individual member the coefficient is 0.
Oh, okay. So you don't have special points or something like this. This is what you're saying that's happening.
Exactly.
Okay. I see. Okay.
So it's not a problem of cancellations. You do not have points.
I see. And I don't know. I mean, probably this won't work. But if you don't have points, maybe we should look at other local thing at P, right? Like in this article of yours with Daniel, where sometimes when you don't have local points because of a local condition, you have to choose the order and go to some Cartan or something like this and try to see whether you have embeddings in these points, and try to see whether if you, instead of taking this gamma naught of something, you took some Cartan at these primes, you get special points. I mean, if the issue is the lack of special points, you should change the level probably. I don't know.
Okay, I'll take that.
I think the issue, in order for this to work, you need to pick an L. The auxiliary discriminant L has to be multiple of this problematic prime. And that's what, so if you don't do that, then there's no special points. But if you put this prime in L, then it would be possible to do. But of course, Sham formula doesn't, you have this issue where your discriminant is multiple of a prime that appears to a power larger than 1 in the level. But in principle, it's possible, and we checked some ideas to even how to define a weight function for that. But I mean, it just gets a bit messy, and we want to get the paper out. So I think in principle there should be a way, but it depends on having a more general Gross-Zagier formula for, you know, when the discriminant and the level are not co-prime. You know, when you have a prime that divides the discriminant and the square of the prime divides the level. So you have to do this computation. So I mean, you know, it didn't make sense to worry too much about the messy weight functions when you don't have the other. I mean, it's only, as far as I know, it's only done for p square over the rationals. The work we did, it's just that. I mean, but anyway.
No. I mean, my only point was that when you have a prime square in the level, you are in the case where you can change your level from gamma naught of p squared to some cartanate of level to the first power in p, right? Mm-hmm. And so sometimes this moving to this other world gives you already special points in this other level. I mean, if the issue is that the special points are not there, maybe just changing the order might help you, and using the same weight function. I mean, instead of having to have a different idea on the weight function, you might have to just change the order, but I don't know, it was just an idea. So thank you.
You're always getting a central value that is non-zero, or what happens when it's zero, or a central value, or the twists are non-zero?
This could vanish, of course, because these coefficients might vanish for non-trivial reasons. I mean, not because of function equation reasons. So this one's going to be non-zero for proper L, because the functional equation for this one is going to be sine equal to 1. So a result of Waldspurger shows that as long as this twist has a function equation with sine 1, you're going to be able to find an L for which this does not vanish. Does this answer your question?
Yes, so there always exists one.
Yeah.
Yeah, because otherwise, I don't know if, can you do things if it vanishes, but yes, so there's always one that doesn't.
Yeah, and we choose L as small as possible because if we are going to count points here, we prefer not to go too far. So in our code, in our algorithms, we start by moving from small to big L and choose the smallest one as possible.
Thank you.
How much freedom do you have in choosing your Hecke character chi? At some point you said you wanted f chi to be as small as possible.
Well, the result's going to hold with you can choose chi completely freely if you want the level of the morpheme that you're building to be as small as possible. You will want this Hecke character to be as small as possible in terms of its conductor, but in principle you have complete freedom. This is all you need from your Hecke character.
Okay. So you can't arrange for f chi to be just 1. There must be some ramification.
Yeah. You certainly you need it to be out at ranks in which the opposite of this condition holds.
I see. Sorry.
So when these do not agree, then the level is not going to be 4n, because you will certainly need to have some ramification character.
Well, if there are no more questions for Nicolás, we can thank him again.